So Friday, we did number 1, and we started 3. So we're going to try to get through a few more today, but tomorrow I'm going to be checking pages 1 through 6. Okay, so we're just going to be, I'll be checking 1 through 6 tomorrow. I have the solution key, all the videos for all the problems online, so I'll send out a reminder this afternoon as well. And then tomorrow, we're going to start looking at the FRQ quiz type problems that you're going to see for Friday. So basically, it's very, we're just going to go through very similar problems that you're going to be expecting to see for Friday's quiz. Okay. And again, each of the assignments I'm giving will go towards your test grade just for fully completing it. And if the work is not to if it's not up to par to what I'm looking for, then I'll give you guys, I'll let you know to send me photos of your work later in the day, and also give you full credit. Okay. Any questions about the plan for assignments and grades? Okay, so we finished number 1, and we made some progress on number 3, but let me recap the steps that we did for number 3. Okay, so number 3 was all about the amount of sand on the beach. We have S of t and R of t. So S of t is giving us information about the rate at which the water, sorry, not water, the rate at which the tide is removing the sand from the beach, and the S of t is the rate at which sand is being added onto the beach. Okay. We knew that we could find the amount of sand that's been pulled from the beach just by taking that rate and accumulating that rate over a period of time. So we're able to transform that yards per hour in terms of yards, cubic yards. Right. And then we know that there are 3 things we have to keep track of if we want to find out the total amount of sand on the beach. There's the initial amount, there's the amount being added, and there's also the amount being removed. Okay. So the integral just indicates that we are transforming each of these to have matching units, right? This 2500 is cubic yards. Integral of S of x will turn into cubic yards. Integral of R of x initially was cubic yards per hour, and we're able to get that to be cubic yards. And then part C was find the rate at which the amount of sand is changing at 4 hours. So anytime I'm dealing with rate, I have to involve derivative. And so I have to first find y prime. To find y prime, I take my y of x, and I just take the derivative of each term. So 2500 goes to 0. Integral of S of x becomes S of t. Integral of R of x becomes R of t. So I'm just taking that integral and just making it drop. So I'm stripping away that integral because I'm taking the derivative of both terms, and both terms are sitting at one level above S of x, and I take the derivative, and that's going to take the integral along with it, just kind of undoing that integral process. So my derivative is simply S of t minus R of t, and I want to find the rate at which the amount of sand is changing at 4 hours. So I enter 4 in for S of t and R of t. So S of 4 minus R of 4 is negative 1.908. So that indicates, that negative number indicates that despite the fact that sand is being pumped onto the beach, R of x is taking away more sand. So that negative 1.908 indicates that the amount of sand on the beach is shrinking by that amount 4 hours in. Okay, so now for part D, Part D says, oh, and then to find S of 4 minus R of 4, you're just entering that directly into the calculator, right? You have S of X, you have R of X, you're just inserting that in manually, or you can call Y1 and Y2 and have just do Y of 4 minus R of 4, sorry, Y of 4 minus Y2 of 4, assuming that you have S and R plugged into your Y1 and Y2. Okay, part D. At what time is the amount of sand on the beach a minimum? So let's talk about that word there, minimum. The understood indication here is that it's not a relative minimum. This is talking about absolute minimum. And if I want to find absolute minimum or absolute maximum, this is the first semester topic here, extreme value theorem. Okay, so let's talk about that for a moment. Extreme value theorem. Okay, so if I want to find absolute minimum, extreme value theorem says find critical points and test them, but then also test your endpoints. We know what the endpoints are because they tell us in the problem the time intervals between 0 and 6 hours. So we're definitely going to test how much sand there is on the beach, 0 hours and 6 hours in. But we also want to figure out where y prime is equal to 0. Okay? Because where y prime is equal to 0 is also a critical point that we have to involve. So if I want to find y prime equal to 0, I just take that y prime from part C and set that equal to 0. So basically, my S of t minus R of t is equal to 0 is going to be a candidate where I can find my critical point. So in your calculator, you can either use numsolve and set S of t equals R of t, or you can set S of t minus R of t equal to 0. And then for in your graphing calculator, you're going to graph S of t minus R of t, and then simply look at the graph to see where it crosses the x-axis. So here's my, well, I have y1 being held by, I have S of t held by y1, and I have R of t held by y2. And I'm just going to graph y1 minus y2, which is basically S of t minus R of t. Notice I'm only highlighting the third graph because I don't want to see the first and second one. And then I'm going to do zoom 6 just to kind of see where it shows up. And if I need to zoom in or zoom out, I can. Okay, I'm only looking to see where is the graph going to cross between 0 and 6. The x-intercept between 0 and 6, and I see a critical point there. I see an x-intercept there. So I'm going to zoom in, see if I can have an easier, well, I don't necessarily have to zoom in. I can just do second trace and look for 0. Second trace 0. So I'm going to pick a point to the left of the x-intercept. I hit enter. Scroll over to a point on the right side of the x-intercept, hit enter. Hit enter a third time. And we get 5.117. So we know that 5 hours in, that could be a potential for the amount of sand on the beach at an absolute minimum. Okay, so now we have 3 critical points. Sorry, we have 3 test points. We got 2 endpoints and we have 1 critical point. So we're just going to take the time to enter into our y of t equation, because y of t can tell us the amount of sand at any point in time, right? It takes into account everything that could impact how much sand is on the beach at any given time. So we'll do y of 0 first. We already know y of 0 is 2,500. That's given to us in the problem. And then the next we can do y of 5.117. So we want to find out how much sand there is on the beach 5 hours in. So I can accumulate the amount of sand added to the beach by doing the integral from 0 to 5.117. I can also accumulate the amount of sand removed from the beach if I do integral from 0 to 5.117 the FR of x. So make the calculator find those values for me, and I get 2492.369. And there's one more point we have to test. We also have to test what happens 6 hours in, because 6 is an endpoint. So we'll do y of 6. So this will accumulate how much sand has been added. This will accumulate how much sand has been removed, plus how much sand there is to begin with. And then we get 2493. And then between these three values, we see the lowest amount is that 2492. So we can conclude that the absolute minimum must be at 5.117 hours. Now this problem says justify your answer, but you don't have to really provide any sentences. If you just indicate that you found the critical point, that you used, you don't even have to state extreme value theorem. You just have to go through the steps for involving endpoints and critical points, and then just make your conclusion based off of it. So you don't have to provide any you don't have to provide any sentences to justify your answer or any because statements. If you just provide this work that is considered sufficient on the AP exam. Okay, let's look at number 5. Okay, number 5. All right, so let's look at number 5, or page 5. Okay, let me go through this problem in detail. There's quite a bit going on here. The amount of water in the storage tank in gallons is modeled by a continuous function on the time interval from 0 to 7 hours, where t is measured in hours. In this model, rates are given as follows. Okay. Number 1, the rate at which water enters the tank is f of t. So we see the rate is increasing over the course of this time period, right? So initially, there's not much water being let in, but then it rises to, 500 gallons per hour, 1,500 gallons per hour, close to 2,500 gallons per hour over this course of 7 hours, right? So you can imagine, there's more and more water being let in, or the amount per time at any given point is rising. Okay, now there's also something else going on here, is that there's also water being let out at the bottom of the tank. So the rate at which water leaves the tank is 250 gallons per hour for the first 3 hours. So it's a constant rate. Okay. And then, but all of a sudden, they're going to turn that up all the way to 2,000 gallons per hour. So a lot more water leaving. So a couple things going on here. The amount of water coming in is increasing at a steady rate, and then the amount of water being let out is at a constant rate, but then it's going to switch up to a lot more 3 hours in. Okay, so they tell us that the graphs of F and G intersect at 1.617 and 5.076 hours. Okay, at time equals 0, the amount of water in the tank is 5,000 gallons. Okay, so part A says how much water enters the tank during the time interval from 0 to 7 hours. So for part A, we're not concerned about how much water there is in the tank. We don't care about how much water has left the tank. We just want to know how much water has entered into the tank. So for part A, we only have to involve what? Yeah, just F of T. So, but F of T is gallons per hour, but we want something in terms of gallons. So we have to do what to it? Take the what? Yeah, antiderivative, right? Antiderivative is essentially going to change that unit. It's going to strip that rate away, and it's going to give us gallons. Okay, you can practice entering this into your calculator. Make sure that you're only using variable x, and also that you're in radian mode, right? Anytime you're dealing with trig, you just don't want to be in degree mode. In fact, you should always just be in radian mode, never be in degree mode. Okay, so before we look at part B, let's see if we can imagine and visualize what's happening based off of this graph. Okay. Let's think in terms of, is the water level rising and falling? Can you imagine the water level rising and falling in each of these time intervals? So let me ask you this. Between 0 and 1.617, what's happening to the water level? Any idea? So this horizontal line tells us that there are 250 gallons per hour of water being let out. And then here, this curve is less than that. So what's going to happen to the water level in the tank if there's more water let out than what's coming in? It's going to lose water. That water level is dropping, right? The water level is dropping from 0 to 1.617 because that horizontal line is more than that curve. Okay. Then what's happening at 1.617? Yeah, it's equal. So if it's equal, that means the water level is going to stay same. Yeah, for just a moment, right? It's falling, but it's going to stay for a moment. And then what's going to happen between 2 and 3? Is right. The curve is higher than the line. So all of a sudden, there's more water coming in than leaving, so that water level is rising. Right? Water level is rising. So I'm highlighting which is winning out in each of the time intervals, right? So the pink indicates that, okay, there's more water leaving than coming in, so water level is dropping, and then water level is rising. But then what's happening between 3 and 5.076? 2,000 gallons of water per hour, and then the amount of water coming in is increasing, but it's not as much as what's being let out. So the water level is going to do what again? It's going to drop, right? It's going to drop because 2,000 gallons per hour versus 1,500 gallons per hour. Okay. And then at 5.076 hours, the water level is going to stay level again. But then after that, the curve takes over. So we know the water level is going to rise again. So water level is falling, stays the same, rises, falls, rises. Does that make sense? Okay. So then for part B, it says between 0 and 7 hours, find the time interval during which the amount of water in the tank is decreasing. So decreasing, I highlighted that in pink, right? So anytime the horizontal line is higher than the curve, then you know that the water level is dropping. And it's simply because G of t is greater than F of t. Right. Oops, F of t. Right. The rate that water is leaving is higher than the rate at which water is coming in. So that's going to impact what's going to happen with the water level. Okay, part C. At what time is the amount of water at the greatest? Okay, the amount of water is at the greatest, so that's an indication that this is, again, extreme value theorem. We're trying to find the absolute max. So to find absolute max, we have to test critical points and endpoints. But for critical points, we only have to test relative max. There's no need to test relative minimum because there's no chance that relative minimum could be a greatest. So relative max here. Okay, water level is dropping, it starts increasing, and then it starts to drop again. So we know that there is a relative max at t equals 3. Because at 3, you know that the water level is going to be rising followed by falling. So you know that there's a relative max here, right? So we just have to test 0, 3, and 7, 3 being the relative max, 0 and 7 being the endpoints. So just like from the previous problem, there's 3 pieces of information we got to keep track of, right? There's the initial amount, there's the amount coming in, and there's also the amount being removed. So we know there's 5,000 gallons to begin with. Integral of from 0 to t of f of x will accumulate the amount of water coming in, and then the integral of g of x will give us the indication of how much is being removed. Okay. And then into this general formula, we can test our 3 points, right? We can test 0, 3, and 7. Well, 0 is easy because they already tell us that there's 5,000 gallons to begin with. So if we try to plug in, we will get that same result because 0 to 0 is just not going to have any impact for the second and third integrals. If I want to find out how much water is in the tank at 3 hours, because we know that's a relative max, 5,000 would be the initial. The integral from 0 to 3 would be the accumulation of water that's entered in, and then 0 to 3. F of g of x is split into 2 categories, right? Or 2 time intervals. From 0 to 3 is 250 gallons per hour, but then from 3 to 7 is 2,000 gallons per hour. So we care about the 250, so we can enter that into the calculator. It's just a constant rate, so that's why that's just a number. Okay, we enter that in the calculator, and we get 5126 gallons. Now, g of x is changing halfway through the problem, right? Because it's 250 gallons per hour, then it switches to 2,000 gallons per hour. So if I want to find out how much water is in the tank at 7 hours, I'm going to just build off of a running total, because I know how much is in the tank at 3 hours, and I'll just go from 3 hours forward, right? Because I know that 3 hours in, I have 5126, and then from there I can just keep doing running total. I know that. Okay, from 3 to 7, I can figure out how much water has entered in the tank between 3 and 7 hours. And then I can also figure out how much water has left the tank between 3 and 7 hours. It's a different rate. So it's nice to be able to split up and just not to count from 0 again. I can just count from 3 hours forward. So this is how much I have in the tank 3 hours in. And then this is how much water has been added between 3 and 7 hours. And this is how much water has been removed between that time period. And that's going to tell me how much water is in the tanks at 7 hours in. So we can tell that the absolute maximum must be at 5126 because that is the largest value amongst the candidates that I tested. Okay, let's also look at number 6 whenever you guys are done. Okay, here's number 6. Okay, the rate at which people enter an auditorium for a concert is modeled by the function R, given by R of t. R of t is measured in people per hour. No one in the auditorium is at time t equals 0 when the door opens. The doors close and the concert begins at time t equals 2. Okay, so part A says how many people are in the auditorium when the concert begins. We know R of t is people per hour. We want to figure out how many people are in the concert hall, and we can accumulate that rate over the course of 2 hours. So that's just taking the integral, right? Taking the integral, we can transform this people per hour to the number of people. So think of it as multiplication, right? You have people per hour times time, and that's going to cross the time out, and you know you're going to be left with just number of people. Part B says, find a time when the rate is at a maximum. Okay, so notice that it's not saying when is the number of people at a maximum, it's saying what's the rate at which people enter is at a maximum. So the rate, we know that maximum means we have to involve critical points to find critical points, and we have to involve the derivative. So we have to set R prime equal to 0. Okay, we know R of t is already a rate, but it's asking for the maximum of the rate, so we have to find R prime. Okay, so we set R prime equal to 0. We know, just like with previous extreme value theorem problems, we're going to find critical point and endpoints. Okay, so set R prime equal to 0. R prime just means find the derivative. I can quickly do power rule there. 2760t minus 2025t squared. Set that equal to 0. You can make the calculator, graphing calculator, find the x-intercept for you, or you can solve it by hand. But you can also make num solve on your 36 Pro. So under Y theory, I said 2760x minus 2525x squared. I just did power rule for those terms, set equal to 0. I only want to graph what I have here. Any previous ones, I just made sure the equal sign was unhighlighted. And window, I just adjusted it from, I can just go from 0 to 2 if I wanted to. I just want to see around my endpoints. I know my x values is only between 0 and 2, so I just did from -1 to 3. And then for Ymin, Ymax, the reason I set such high numbers is because my values are in the thousands. So otherwise, if you have your Ymin, Ymax being just -10 and 10, it's just going to look like a straight line because you're zoomed in too far in. So here, if I do second trace, 0, I can pick a point to the left of the x-intercept and then scroll over to a point on the other side of the x-intercept, hit enter. So there's my critical point. I know that that's a potential maximum. So EVT, I got to test endpoints and critical points. So I need to test R of 0. I need to test R of 1.3296. I need to test R of 2. So we just entered 0, 1.3296, and 2 directly into R of t. And see which one produces the highest rate. So 0 would give us 0, because we know that at 0 hours there's no one, there's no one in the concert hall, so in the auditorium, so the rate is still 0. 1 hour in, the rate is 854 people per hour, and then 2 hours in, it's only 120. So you can tell that the max rate is obviously 854 because that's the largest number amongst the 3. Thanks. Okay, part C says the total wait time for all the people in the auditorium is found by adding the time each person waits, starting at the time that the person enters the auditorium and ending when the concert begins. The function W models the total wait time for all people who enter the auditorium. So the derivative is given by W prime. So find W of 2 minus W of 1. Okay, so this is what they tell us. They're not giving us the wait time. They're giving us W prime, the rate of the wait time. But ultimately, they want to find out what's W of 2 minus W of 1. So the question is, right, how do I link these two together? This is at the derivative. This is at the integral. And this is at the function level. So we got to take the integral, right? Well, we have this to work with. This is a rearranging of the first theorem. First theorem says the integral from a to b of W prime, it's just going to be W of b minus W of a. Right. If I take the antiderivative, I can just plug in the upper and lower bounds. So that's the connection right there, because the integral of W prime from 1 to 2 is going to give us W of 2 minus W of 1. So if I simply take the integral of W prime from 1 to 2, that's going to tell us the total wait time that that people have to experience. So we just enter that in the calculator. Plug in the RFT. Okay, so I'm going to check this tomorrow, 1 through 6. I'll send out a reminder. Okay. So homework, finish the rest of pages 1 through 6.
So with sketching, I don't even know what I'm
Thank you.
finding. So is there any way you can like figure out like, what I need to feed and how I should do that? 'Cause I can't write. I probably will have to have surgery. So I tore it. So, but yeah.
Thank you.
So